Yeah, we started out doing ECSEs, maybe 4 years ago, and now just last week hit 3,500 students, so 3,500 is good. About 120 classes this year and over 150 scheduled for next year. So people like it, and so they keep coming, and we keep teaching, and so thanks to all of you who decided to do that, and I'll stay away from the speakers. So, anything else you need?
No, next year there's going to be even more advanced stuff, right?
Yes, and we can't. He can announce things and no one else can. I can't say it, but whatever he said, yes.
Yeah. So more advanced stuff coming up next year. That's pretty exciting.
More advanced stuff, more classes, more fun things.
One more thing.
He was holding a fake microphone there. Did you see that? He was actually pretending.
Yeah. So this guy hosts the best Wi-Fi conference there is, called WLAN Professionals Conference, and the main event happens next February. It's every February in Phoenix. It's a bit hard to get to from Finland, but that's okay. Not that I would mention that to the man, but do come there. It's the best Wi-Fi event there is. There's a lot of good ones, but it's just the best. And there's like about 300 people just talk about Wi-Fi.
It's like this for 3 days or more. So we just like hanging out with other Wi-Fi people. So actually, this Wi-Fi Design Day is a good tease to see if you like that. If you have a community built together, we will bring a conference and have more fun. He's the swag giver. Giver of swag. Well, they asked if I'd come and talk about how Wi-Fi, how to make Wi-Fi that works well. We like Wi-Fi that works good, and there's Wi-Fi that doesn't work so good. And so I kind of renamed this because Wi-Fi always works. When I'm teaching class, people go, well, we get this huge complaint about Wi-Fi is slow. And as soon as they say that, I go, what you just told me is Wi-Fi is working. So I changed the title to be Things I've Learned About Wireless from Teaching Hundreds of Classes to thousands of people. And in that process, I hear lots of people talk when they come, and I see what they've learned before and after. And one of the biggest things that happens in class is they leave going, I did not know that. Which is great. I mean, as an instructor, if you learn something in class, that's the best compliment I can ever receive. But I've had about at least half of all the CWNEs in the world, of those 300 UC was talking about, go through ECC class, and when they leave, they're like, I did not know that. I didn't know that's how it actually worked. So, let's get started. My name's Keith. You can find me on Twitter, Keith R. Parsons. My website's WLANpros.com. We have lots and lots of free stuff. I'm known for saying knowledge is like manure, and the stuff that comes out of the back of the cow. If you spread it around, it helps things grow. If you hold on to it, you just stink. So, we want to spread stuff around, so everything on the WLAN Pros website is free. We have hundreds and hundreds of dollars of videos, of white papers, supporting documents. It's just a place to go get resources. There's also Twitter roles, so if you want to find people to follow on Twitter, follow on Twitter. When I teach class, I normally have people say, how many of you are not on Twitter? And while you're on, come on, how many people are not on Twitter? Leave your hands up. I hereby swear. I will join Twitter today. The next question, how many of you do not have a blog? I hereby swear I'm going to start a blog today. There's reasons you use blogs and there's reasons you use Twitter. I use a blog because I have a really small brain and I can't remember things. And I thought it was unique for me that one day I was Googling something to find an answer to a question that was technical, and lo and behold, up came up my blog to answer my question that I had obviously forgotten, because you can't hold it all in your head. So as you're learning and you find a new thing, put it in the blog. Your blog is like, let Google be your search engine inside your head, and then you don't have to remember things. It's a great service. I thought it was just me, And I was at a conference actually made up of bloggers, and I made that comment. I Googled myself, and my own blog came up. 100% of the bloggers said, happens to me all the time. So treat the blog as just a way to keep your memory. But the cool part about a blog and community is you're sharing your brain with other people at the same time. And so when you do have a question, you can find someone else's blog, take it, learn from it, and continue on. Sometimes people ask me, well, how do you get involved in the community and get started? And the easy answer is you go follow me on Twitter, follow lots of people on Twitter, and on Twitter, don't post what you had for lunch. No one cares. But if you post a technical question to a technical person, and engineers have a tendency to have big egos, and you say, how did you do X, Y, Z? Or I have a question, and ask a smart question. If it's a question you could find your own answer for, then why are you asking some expert on Twitter? But if you ask it a legitimate, intelligent question, they will probably, especially it's Twitter, send you a link. You can go, it's right here. That's perfect. Because now your job is to go to the link, research it, find your answer, write a blog, tweet back to the person who gave you the link and say, hey, I followed your advice. I did this, I read this, I now have this blog post, and I'm going to guarantee you that person is going to retweet your message. Because you just complimented him. He told you something, and you did something with it. You just didn't run away and go, oh, no, you did it. And now you're going to share your information with others, and he will gladly help others share your information with everyone else. And you're going to engage in the community. Don't be just a troll sitting on the side sucking stuff off. You don't have to blog very often, but when you do, share it with others. Okay, enough about getting the community started. Wi-Fi is really, really easy to do wrong. Like, it's incredibly easy to do wrong. It's also not scalable. You can go, I was going to say Dick Smith, but they're not around anymore. But you get the idea. You can put it in Dick Smith, you buy yourself a Linksys, take it home, plug it in, you're flat, and you have good Wi-Fi. Kind of. But you have a very low threshold of what you need. And the reason it is easy to do wrong, answering my why question, because even if you don't know anything about best practices, you don't know any about the rules we're going to cover here, and I've got about 50 rules I'm going to cover in the next hour or so, Wi-Fi still works. Wi-Fi always works. It might not work the way you want, but just about always works. I get paid to fly all around the world and fix Wi-Fi. I have not, in the last decade, seen a coverage hole. At a Bedouin camp out in the desert, 100 kilometers south of Dubai, no coverage holes. They had Wi-Fi. I have yet to be in a hospital for 10 years that I have seen a coverage hole. Now, I've been in a lot of hospitals where the nurse says, yeah, I dropped right here. And when you come to find out, you ping to their little WOW, their little computer on wheels, and the ping is still going, and they go, see, it dies right here. And you say, why do you, I'm pinging it, it's obviously alive. And you say, why did you think it died? Well, it made me log back in again. But can you use your phone here? Yeah. Here's my phone. It works, yeah. So actually, your cow is pinging right now. It's working on the Wi-Fi. Well, why is my app not running? Now that's a really good question. It has nothing to do with Wi-Fi. If it's a Wi-Fi problem, we know it's a Wi-Fi problem because it's a Wi-Fi problem. It's not a Wi-Fi problem if it's not Wi-Fi, but our users don't know that. So anything that's on Wi-Fi is going to have a feeling that it's a Wi-Fi problem. When they say Wi-Fi is slow, Wi-Fi works. They say Wi-Fi sucks, Wi-Fi works. I just got hacked on Wi-Fi. Wi-Fi's obviously working. So we need to follow some rules. We might call them best practices. I have a whole bunch of ones we're going to go over here. I'm not going to, I could spend 4 days going through every single rule. I'm just going to go really fast. Hopefully you're going to spark something in your head and you're going to go, yeah, I follow that rule, or I totally disagree with Keith. He is absolutely wrong. Good. I like to be wrong. I try to make sure every one of my statements has some supporting documentation for it. It just might not be the same supporting documentation you want. Or you get paid for doing something, and I don't get paid for doing that, so we have a disagreement. It's all about who gets paid for what. So, let's go through a couple here. Well, first get started. There's some rules in the world. This rule is from a guy named Kawasaki. Guy Kawasaki used to be evangelist at Apple, and he has the 10-20-30 rule for a presentation. No more than 10 slides, 20 minutes of talking, everything else is Q&A, and make sure the font's 30 points or bigger. That's his rule. And I'm going to break it. I had way more than 10 slides. I'm going to talk more than 20 minutes, but I made bigger than 30-point font. I was going to offset, because he went on 30, I went to 80s or 90s. So first, let's talk about rules. I was a little kid, lived in Norway, and this was in the 60s, a long time ago. And we had Legos, and back then they didn't have any of the fancy Legos. There was just bricks. That's all they had. And so if you wanted to make something up, you made it. And my mom would invite her friends over to have, I don't know what women did, they talked. And they would bring little kids with them. And she's like, go play with their kids. I'm like, I'm playing Lego. This is serious. No, they don't know how to play Lego. Play with them anyway. And so I'd have these other kids come over, and they did not know the rules of Lego. And I would, Mom, they're breaking the rules. Play with the kids. So, here's an example. Let's say I had a requirement, and obviously this is an analogy for Wi-Fi. So in Wi-Fi, we might have a requirement of something. In this one, I said, I want to use Lego. I want a house that's 8 studs by 16 studs, so it's a rectangle. It needs to be 4 bricks high. It needs to have a sloped roof, but the roof needs to go sloped lengthwise. But you have a limited supply of bricks. Go. And my newfound friend who didn't know how to do Lego would do something like this. Now, anyone who's done Lego before is going to obviously see what's wrong. What's wrong? It'll fall apart. How do you know? You just know because you have an engineering soul, and you've done it before, and it broke for you before, so you know don't do that thing because it's a dumb thing to do. You don't stack these vertically. There's no support. But it meets all the requirements. So in Wi-Fi, you can have someone go, we need Wi-Fi coverage, and the coffee shop needs this and this and this, and then you break every rule in the book. You put APs where they shouldn't, you mount them sideways, you put them upside down, you have high power, low power, you break everything that should break. It still meets the requirements. So here is what happens when you use all the same materials, Wi-Fi, radios, channels, Ethernet, but you break the rules. It just takes nothing. It's brittle. I don't want a brittle system. I want a robust system. Instead, if you follow design rules, and that's not as pretty, it's got these little Z things going on, but now I have the same number of bricks in the same shape, and a big fat guy can stand on it and it doesn't break. And the only difference is I followed the rules. I used engineering principles rather than sales principles. It looked pretty. But it broke. This is not so pretty, but it's really, really strong. So this presentation is about how do we make Wi-Fi that's robust, still meets the requirements, still costs the same amount of money, same number of bricks, same parts, but we want to do it right. Thus, we need to engineer solutions. Now, I use the word engineer on purpose. I just didn't say design, I said engineer, because when you hear the word engineer, you think of math. Wi-Fi has a lot of math. And if you're afraid of math, use a tool like Ekahau that does all the math for you. I get this silly question, people go, hey, you use the Ekahau thing a lot? Do you trust it? I'm like, do you trust Microsoft Excel? They're like, what? When you put in 17 in A1, 3 in A2, and in A3 you say A1 times A2, do you think it's not going to come up with the same number every time? I mean, either you trust Microsoft Excel or you don't. If you trust Excel, you trust Ekahau, because Ekahau is just taking one cell of information, this cell. Now it's more complex. It's logarithmic math. We can't do that in our heads. It's RF math that's changing attenuation in the wall. And if you put in the wrong wall attenuation, Ekahau is going to give you the wrong answer. But that's not Ekahau's fault. That's your fault. You put the wrong thing in. About engineering. If you were, you know, your wife comes, you come home and your wife says, can you build a doghouse for our dog? And you go, we have a dog? Yeah, we got one for the kids, but we need a house. You can go down to your local DIY store. You maybe on a napkin draw something up. And you can build a doghouse. You buy some wood, some nails, boom, you got it. At small scale, it's easy. You come home one day and your wife says, we just bought some horses. We need a barn. You're not going to the local store and buying little wood and screwing it together. You call a structural engineer and they do math to figure out what's the span, how far is it going to go. And I bet there's not a structural engineer in the world that would look at this room and say, yeah, I think you should have one beam per room. But I know lots of sales guys, one beam per classroom. Why? Because I sell more that way. Does it meet requirements? I don't know. It's just easier. This is easy. That needs math. Another example. I was hunting around, and I live in Utah, and the Salt Lake Airport is just being expanded. And one day I saw this. So I went to a picture of it, because it's very indicative of how Wi-Fi works. This, on the other hand, and that are both rebar. One's engineered, one's said, let's just stick some stuff in the ground and find out. When they're covered up, you can't tell which one's going to fall down. Now the fact I took this picture, and then 2 weeks later the Salt Lake Airport had to tear it all down because someone used the wrong formula of concrete that breaks when it gets cold. And in Utah, our license plates say the greatest snow on earth. And so probably not a good thing to have concrete that doesn't cure well in the cold. But the insides we're not going to see in the future. You engineer a solution and then it's robust. This may work fine. And if it's for a little house, great. But if you're building a whole parking, this is from a parking garage, 7th floor stall, you better get the math right. So let's go and talk about some rules. We should follow these rules or break them. In fact, every single one of the rules I'm going to tell you, there's totally legitimate reasons to break it. But you need to know what the rule is first, know why the rule exists, and know why you should break it. So I have no problem breaking the rules. I break most of these rules all the time. But you need to know what it is before you go around and break it. If you break the rule and you didn't even know it was a rule, it's like if the tree falls in the forest. Don't say the word survey. Now, if you want to say survey, I don't mind the word survey. Survey is a good word. I use it all the time. It's built into Ekahau's name. Ekahau Site Survey. It's a tool. But don't use survey when you mean to say design. Because your customers go, oh, you mean you're going to walk around? I don't have to walk around to do a design. If I do AP on a stick and I walk around, the only thing I get is coverage. And coverage is easy, so that's a big deal. I don't have to walk around in order to do design. Now it helps to go on site and measure walls. It helps to go on site and find out where the IDFs are, where the cable runs. There's a lot of reasons for being on site. But don't call it a survey, call it design. Because it's design work. It's engineering work. Just the part of walking around isn't it. On the other hand, if you're going to do a survey, do a survey. Actually go and measure every time you install Wi-Fi. If you don't do a validation survey, how do you know if it's working? You're just guessing. People who pay have no problem paying a cable contractor to pull in Cat 6 cable. And have you ever known a Cat 6 cable contractor to go on the spool on the truck in the parking lot, measure and say, it's Cat 6, and then install it? When do you validate Cat 6 cable? This is the part where I ask the question you answer. When do you validate Cat 6 cable? After it's installed. So when should we validate Wi-Fi? After it's installed. This is not a difficult question, guys. Okay, so we want to engineer engineer is the primary word here. Don't use simplified marketing. If there is a ratio involved in what you think is design, it's not design, it's sales. So if someone says, we want 1 AP every 300 square meters, that's a ratio, X per X. I can tell you right now, that is not a design, that's sales. Well, from the last 10 jobs we did, we averaged, you might have averaged, but you still figured out. Would you trust an architect who said, yeah, we were designing this building with this beam above us, and you know the last 10 we did, we kind of put 2 beams every 20 meters. And then this has a 7-story building on it, and the last one you've been doing single stories. Oh yeah, no. Structural engineers do it every single time. You have to do the math over and over. You need to know all the requirements. I admit freely, 15 years ago, I used amplifiers on my Wi-Fi. 30 dB amplifiers, because I thought it was all about coverage. And then I got to be an expert witness for lawsuits, and we kept suing systems integrators, and we found out, you know what? Just because you have coverage doesn't mean Wi-Fi is going to work. And I thought it was. And all of a sudden you realize, yeah, I can make my APs yell really, really loud, but I can't hear any of the clients. And just because you can hear me, I can't hear you, that's not good Wi-Fi. So know all your requirements. There's a bunch of requirements, only one of which is coverage. And if you don't make all of the requirements in your design, then you're going to fail. Oh no, you're not going to fail, because Wi-Fi always works. You can't design for all Wi-Fi. I know you go into your customer, you say, let me borrow your paper for a second. Not you, a sales guy does this. Where do you want coverage? Everywhere. What clients do you want coverage for? All of them. You can't. You cannot design for all clients. In fact, I'm going to show you in a couple of slides why. But you can't. You can design for one. Now you got to pick the right one. If you pick the wrong one, bad things happen. I had a customer once who I said, pick the one thing you want. And they said, which one? I said, pick the worst one. Because if we get the worst one to work, everything else will work. We did. We installed it. They had me design for a Galaxy S3. Any S3 victims? It did not have good Wi-Fi. And they picked it and I said, are you sure? At the time, there was S6s around. They said, no, you said the worst one, S3 is the worst. And we're all done. I was given a report and I explained at the very last slide, it works fine. We tested with S3s. In fact, the S3 is still on my shelf in my office. But you spent $100,000 too much. What? Everyone freaked out. Why did we pick the S3? I don't know. You picked it. I didn't. But if you pick the wrong one, you're going to have to support something old. And do you think in the future, an iPhone 14 will have better capacity than iPhone 10? If you just go back in history, you're like, oh yeah, they keep getting better, not worse. So every time I have to go backwards in my design, my cost goes up. Older phones cost higher infrastructure today. So when your customer says, oh, you go, really? iPhone 4s? iPhone 5s? iPhone 6s? iPhone 7s? I use iPhone because they have a very nice count. Actually, 5, 5S, 6. Now, which one do you pick? Well, we want to pick one called LCMI. LCMI, famous term, not really famous, but a friend of mine, Devin Aiken, coined it, which is least capable. That's the one I did with the S3, except we also have to say most important. And there was no way the S3 was the most important device we designed for. So if you pick the right LCMI, the whole rest of the design is way easier. If you pick the wrong one, you might have trouble. So spend a lot of time picking this guy. Use the widest channel you can. 160s are better than 80s, or better than 40s, or better than 20. So the rule is use the widest channel you can until you can't. You'll know I have this kind of theme going on. Do this until you can't. Because every rule has reasons you're going to break them. This reason is you can't when you get co-channel interference. If I can design this building and put in 14 APs and they're all 160 meg channels and they don't interfere, 160 meg channels is a good answer. But if they interfere, then I should go to 80s. If the 80s interfere, I should go to 40s. If the 40s interfere, I should go to 20s. Now some people shorten this rule and they just say, always use 20s in enterprise. Why? Because they don't know how to do the measurement. 40s are always better than 20s. if you can do it. If you can't, then use 20s. How do you know? You have co-channel interference. Use the highest minimum basic data rate, MBR. Use the fastest one you can until you can't. How do you know you can't? You get retry rates. If you're not measuring retry rates, don't change your MBR. I've had sites that at 6 was the sweet spot. Push it to 12, check your retry rates. Push it to 18, check your retry. Actually, I don't like 18 because it's a weird number. Push it to 24, check your retry rates. And what's going to happen is if you're looking at your average data rate, that's the average between all the clients together, when you go from 6 to 12, duh, the average goes up because you don't let anybody touch 6. So you're going to watch your average data rate climb, which means your efficiency on your network goes up. It also means your density can go up. This is good stuff. And you keep pushing that, and the average climbs, and the average climbs, but watch your retry rate, and sometimes it's going to go, and sure, I went up to 48, and I have a faster average data rate, but I had my retry rate went hit 50%. Okay, I pushed it too hard. Back down, and you found your sweet spot. If you're not doing the test, don't mess with it, because you might cause harm. But if you're not measuring the harm, how do you know? So for all of these rules, there is the rule, there's an exception, and there's probably a metric that you're going to use to make sure you made the right call. Use the highest possible transmit power. And all of the Cisco guys in the room went, a couple of Arubas too. But you didn't finish. Use the highest transmit power until you can't. How do you know you can't? When my average data rates drop. If I pushed it too hard, now my average goes down because I'm attempting and I fail and attempting and fail and attempting and fail. By the way, if anyone ever tells you to match transmit power from your AP and your client, they're trying to sell you more APs. And it will work. And when they're done and they can say, see, it worked, you should laugh and say, it always works. Wi-Fi always works. Wi-Fi, by definition, thank you for prepping this before, if you understand the protocol, I send you a data frame, what do you have to send me back? An acknowledgement. There is no one-way communication in Wi-Fi. There's no communication. I send you a data and you don't send me an ACK. Or I send you data and you send me an ACK. The ACK is the two-way communication. What could easily happen is I have a mismatch. I talk to you fast, you talk back to me slow. Right? Well, I don't like mismatches. So we can do things to fix it. We can lower our transmit power. We can make sure these get better. But that doesn't mean it was wrong. Keep the highest transmit power, because if I give you a strong transmit and you can talk faster, you use less time, I have higher density. You get density by speed. You don't get density by adding more APs. See? Transmit power does it to you. But if I push the transmit power too high, you can't talk to me and I can't talk to you, and now when you talk back, you talk really, really slow. Now you're using up more airtime, which means the density went the other way. So do it, don't just guess, do it when it gives you a positive result. Always use DFS channels until you can't. Now you've seen the theme here, right? How do you know you can't? When you go check the event log and you see them. Now every manufacturer I know, I'm not trying to single anyone out. What? No, that is wrong, because I have 48 here on the counter. Are you giving me? Okay, thank you. She's like, what? Wrong thing. If you look, and every vendor has DFS events that are false positives. Now the reason for that is the way you have to get approval from FCC. You can't afford to fail, because if you go and you miss that, it might take you 18 months to get back to the cycle, and that's 18 months of R&D you never get recouped. So they're very, very sensitive to make sure we always pass, which means they're ultra sensitive, which means they're probably going to have more false positives. If you had a real DFS event, every AP on that channel and the whole building will go off at the same time. It doesn't matter if you have false positive. If you have DFS events and they're continually happening on the channel, pull the channel out of your channel plan and just make it go away. This one I need my drum roll. Don't use RM, don't use ARM, don't use channel fly. Duh, until you know how to use them. I get so many people who go, yeah, I went to the stupid ruckus hotel and every single channel was on that don't channel fly. That just tells me somebody turned channel fly on as defaults. I can say the same thing about Cisco. You go in and you set the defaults in RRM and you're gonna have a really sucky Wi-Fi. But if you know how to tune it, go ahead and use it. If you don't know how to tune your ARM, static it, because that will force you to think. If you want to use ARM, go ahead, it's a fantastic tool. Just use it right. Don't use the same SSID across frequencies. I want 1.24 and 1.5 gig. Apple, big bright Apple that has hundreds of RF engineers working on their things, came back and recommended, don't use one SSID across frequencies, because from our client side, we can't figure out which one to use. And if Apple, with all the resources, can, nobody else can. Split your SSIDs into 2 SSIDs. And people go, but you said we should only have fewer SSIDs. Yeah, but if I have 1.24 and 1.5 gig, I still only have 1.24. Whether it was the same one on both is with my point. Don't swap out 1-for-1 access points. We had G's, and so we didn't want to pull any more cables, so we put in N's. And now we want to go to AC Wave 2, so we just replaced them. Yeah, they don't look the same. They don't act the same. But you know what? If you do it, Wi-Fi will work. Because Wi-Fi always works. Choose antennas you want that cover what you want, while not covering what you don't want. I would, these slides are going to be available. But you can feel free to take pictures. I will step out of the way because you really don't want to see me. Pick the antenna that covers what you want. The problem with antennas is I can always, 100% of the time, design better Wi-Fi with external antennas. Just cost more. Vendors sell anywhere from 85 to 95% of all their APs are sold with internal antennas. Not because it makes better Wi-Fi, because it's just easier. Just know you can. I've rarely had to build Wi-Fi in round rooms. Any of you design for round rooms? That's the one place Omnis will work. Everywhere else, they're either going to not go to the corners or they'll build it into the next room. You can fix that with antennas if you do. For those of you who, yeah, this is my bugaboo. I've been on Twitter fighting this a long time. Customers want fast, free, and frictionless internet. That's what they want. If you're going to offer public Wi-Fi, don't use a captive portal. There is no benefit to the end customer of a captive portal. There's benefit to the people who want to steal all of their private information and sell it someplace else. There's all sorts of benefits, but it's never to the customer. If you care about your customer, don't have a captive portal. It doesn't matter. Apple cares about their customers a lot. You can go to any Apple store in the world and it's fast, free, frictionless, no captive portal. Except for Macau and Italy, because they have legal laws that require you to have a captive portal. Every other country in the world that has an Apple store doesn't. Disney, you go to Disney, no captive portal needed. They care about their customers. It's a customer issue. Oh, I missed a slide here. I need to do another one. Never rate limit your Wi-Fi. If you rate limit your Wi-Fi, you're rate limiting the thing we have the least of, airtime. So if I rate limit you, you go slow. If you talk slow, fewer people can use it. If I turn on rate limiting, my entire network on the Wi-Fi goes down, and the purpose was to somehow make it go up. So if you care about this, I interviewed a guy named Jim Palmer who runs Denver's International Airport in a podcast about a year ago, and he talked about how they turned rate limiting. They made it 20 mega per person, 10, 5, 2, 1, 100. They got down to 100K, and it just didn't make their network better. And finally he goes, hey, Keith said this crazy thing about turning it off. They turn it off, and within 2 minutes, their network is humming better than it ever had before. Because it's about Wi-Fi. Know your protocol and understand I don't want anyone to talk slow in the air. If you're going to be in an airport and you're going to download a Netflix movie, you click it, and if it takes you 40 minutes or it takes you 2, you're going to use the same amount of packets. One, you're going to use a lot of air time, and one, if I give it to you as fast as you can take it, you'll get off my network. It's the air time we care about. Don't believe marketing hype. This is just it's not a real rule. It's just me. Always do a validation survey, or how do you know what's going on? Always do a passive survey. You have to do a passive survey in Ekahau. You cannot do it active without a passive. Thanks, Ekahau, for making this smart move. In other products, you could have done an active and not a passive. You always have to get a passive. And don't filter the passive. If I say, I don't want to listen to my SSID in a passive, guess what? You'll never see all the coaching interference for your neighbors. And you should report over your customer, look at this, no coaching interference. And you just lie. Do active surveys. I like active surveys, but you better know what they're doing. If you don't know the answers of an active survey, they're going to confuse the heck out of you and your customers. Every time in an active survey and I roam, I'll have a dead spot. So what happens? The client in Wi-Fi is talking to one AP, I am pinging, I stop, I move to another AP, and I'm pinging again. I'm going to lose pings. And when I take something that happened when, and I put it on a map where, it looks like this is a bad place, when there's nothing wrong with this place. Now there's nothing wrong with active surveys, just do them properly and explain it and understand it. Just don't go, yeah, that's a bad place. Now I admit, I used to sell APs to people because when I did an active survey, there was a little red spot. I said, you need an AP there, because obviously it was bad. And it wasn't, it was, I feel guilty now. Green does not mean good. What does green mean on a survey? Absolutely nothing. Doesn't mean anything for a client. I don't know a single client whose roaming algorithm says, I want green. It's not one of the choices. Green on most surveys, when you put it, says, show me all. Or even if you say, show me my APs, you see only mine, and it's all green. You go, that's good. But what does it mean for the individual client? It doesn't mean anything. I have customers all the time who have me come in and fix and troubleshoot, and I come back and say, look, you're all green. And you went, yeah, that's good. Well, why'd you call me? Well, the Wi-Fi's bad. But the survey's all green. I know, yes. But why'd you call me? Because the Wi-Fi's bad. One more time. It's all green. Oh, wait, green doesn't mean, oh, yeah. If it moves, wireless. If it doesn't, wired. That's a really good mantra to keep going until you can't. And it can't could be a budget thing. Sometimes it's hard to wire something, even though it doesn't move, a temperature sensor down in somebody's basement. Maybe wireless is a good choice. But realize it's what does it need? It has different requirements. IoT devices have different requirements than laptops or phones. So just give them what they need. I suggest always using top-line access points. As we saw earlier this morning from Mark, a 4x4 AP outperforms a 3x3 every single time. It doesn't matter if it's talking to a 3x3 client or a 2x2 client or a 1x1 client. The higher end APs outperform lower end APs, meaning you're going to buy fewer of them. They always outperform. Because if you didn't know this, if you go inside the product management part of some vendor and they're making a new AP, a new AX AP that comes out, they get the very best components, the best chips, the best resistor packs, and all the pieces, even the front end modules and the low noise amplifiers, and they're looking at it all and they buy the best parts and they design the best possible Wi-Fi they can. And then they go, wow, that's the top line AP, it's kind of expensive. We think our market wants cheap APs. So they take the list of parts and they go, well, what can we place it that with? Well, this one's worse, but it's cheaper. And this part, and this part, and this part, and they go all through the parts and they knock down the COGS, cost of goods sold. And they come up with a 3x3 AP. Not as good as the 4x4, but cheaper. And then they go, okay, but we need it even cheaper still. One more time. They go through the list and they purposely choose bad components. It's the only way to get the price down. And so when you go buy a 2x2 AP, it doesn't perform as good as a 3x3 or a 4x4. Why? Because they made bad choices. Now, it wasn't a bad choice to get the price down. It's a bad choice. If I want good Wi-Fi, I want good Wi-Fi. I see people all the time go, let's put the high-end APs where we have high density, and then in the low density areas we're going to put the cheap APs. Really? Why would I want to put a cheap AP in when the good AP outperforms the cheap AP? And I need fewer of them. And if you count the whole TCO cost of ownership, the top line AP uses fewer APs. The cheap ones have more APs. Now per AP cost is lower, but I have switch port, PoE, cabling, install, licensing, support. And when you do the math, you go, oh wait, the expensive ones cost my customer less. Don't put access points in hallways, ever. Okay, I break this one. Not because I want to break it, but if you're in a cruise ship and they're little metal boxes and the best way to get in the room is to put one on this side and shoot it across. patch antenna on one side, punch through the steel into the room. It's an AP in the hallway. But that was a very specific use case. Most of the time, if you put them in the hallway, you have worse. The best thing I like showing customers, especially hotels, when they go, we have to put them in the hallways. Why? Well, because we got to, we can't go back in that room. And I said, well, you know what the MTBF is? I don't know. Scott. What's the MTBF on a Aruba AP? 54 years. What's the MTBF on a dirty towel in a hotel? 1 day. So when somebody says, oh yeah, we don't want to go, yeah, you're in that room every day anyway. That's not an excuse. But then I show them, if you put APs in halls, you need more APs. I have yet to have a hotel come back and say, don't put them in the rooms because I saved $100,000. I want to spend $100,000 more. No, they think that in the hallways is cheaper when it's actually less. Don't put access points above the ceiling. If you do, Wi-Fi will still work. It'll just work slower. But you won't see it slower because what happens, you put the AP above the ceiling, I have increased multipath, but I have lower spatial streams. So down below, I'll get the same number of bars, I get the same RSSI, but I won't get the spatial streams, so I lose half my throughput. By just flipping it up and putting it slightly above. It's a huge difference in throughput because someone said, but they're ugly. I don't know about you, but I think exit signs are pretty ugly too. And sprinklers and all those things. They go, well, the sprinklers have to be down because that's how they work. Okay, but oh, I got Legos all over here. So when they say the sprinklers need to be down, I said, no, they don't. You can put the sprinklers above the ceiling tiles. What? Yeah. What happens to the fire? Well, the sprinklers will go off and they'll fill the whole ceiling. They'll fill full of water and then whoosh, you'll put the fire out. Okay, it's not very efficient, but it puts the fire out. We can put our APs above the ceiling tiles. Yeah, it'll work. It's just not as efficient. Don't put the APs on the wall like a clock. Why? Because you lose 6 dB. Boom. I don't want that. I have polarization that's vertical when I put on the wall, and I have horizontal polarization. I lose some dB. Why would I want to have any client have fewer dB? I have fewer dB. I slow down my QAM. I slow down my QAM. Everyone talks longer. My density goes down. You make one thing and it ripples all the way through. Not to mention my antenna pattern changes. Now you might see this on something like SpiceWorks, where guys who are highly qualified, if they're on SpiceWorks by definition, and they go, I did a whole hotel, I did a whole school with these, and I mounted them all on the wall like a clock, and then they answer, but it worked. And the problem with Wi-Fi is when you do it wrong, it works. What if I took a Cat5 cable and I swapped pairs? It won't work. So the instant you make a mistake in Ethernet, you get punished. In Wi-Fi, you do something stupid like this, and it still works. And so you do it again and again and again. Do place them as close as possible to your clients. I would like mine to be down at waist high, because that's where most computers are. Okay, we have vandalism problems, we have problems accessing it, but the rule is as close physically as you can, because the earlier presenter had that little free space loss curve. If I can slide up the curve distance, I get stronger SNR, faster QAM, higher density. Keep access points 2 meters away from anything. From a wall, from a beam, from another AP, from a cellular BTS thing. Yeah, you might have to break this one. But when you go in, make this as your default. I'm going to try to stay away from things. There's a whole bunch of weird stuff you don't need to know. Just follow the rule. When I have my installers do this, I just tell them this rule. And they're cable pullers. They know nothing about Wi-Fi. They just go in the room and go, I have to put it in this room somewhere, 2 meters away, 2 meters away. Okay, I'll put it right there. And in K-12, I just give them one extra rule. There's the first rule, second rule, rotate it so the lights show at the door. So if I do have troubleshooting, I can look through the window and I have to go in the room. That's it. If you use software like Ekahau or Magnet or Tamosoft and you show the AP, most of the time you can move an AP 4, 5, 10 meters, it makes no difference. If you have to put an AP within 1 meter accuracy, don't. Because I don't know any installers who have 1 meter accuracy. So you're not going to get it anyway if you think. Don't place your access points behind, near, hiding, with, close, next to any metal grids or girders. It just, duh. On the other hand, you're doing a warehouse and there's just one metal girder, I gotta go up there. Well, how do I get it down from there? Well, I like to hang them with a little wire, and so if forklift guys, you know, they're on union wages and they hit them and they fall down and they don't have to work anymore. So I see lots of APs with dents with the forks that kept hitting them. I accidentally came across one once in New Orleans after Katrina, where every AP in the whole warehouse was broken on the ground except for one. And the guy was so mad because it was his zone and he's the only one that had to work. And when I go in and it's up there and it is dented, it has marks all over it, and it's just hanging on its Cat 6 cable, Cat 5 cable. And every time he hits it, it just swings out of the way. So we just went to the store, bought some little Kensington lock wires, and sprung them to the cables and let them all hang. In fact, there's vendors who sell spring-mounted arms that you put the AP on it and it goes, boing, comes right back to where it's supposed to go. Man, forklift drivers hate you when you do this. Don't do weird things with your antennas. You ever seen antennas like this? They're always in marketing pictures. Because the marketing guys go, that looks stupid when they're all straight. Let's make them look like a spider leg. Let's make them... Why would you do that? You want your antenna patterns to cover the same areas. If I have one cover one area and a different cover a different area, I just went back to a problem. Why would I want to induce problems in my network? Designed for 5 gig, 5 gig rocks. We have way more frequency, way more channels, way less interference, way, it's good all the way around. But then you're gonna have to turn off a whole bunch of your radios. I shoot for 2/3. Actually, I shoot for 3/4. I would like 3/4 of my AVs turned off. Part of the reason for that is we only have 3 channels. I know you live here and you can go to 13, but we still only have 3 channels. Because if I'm on 6 and you're on 5, we have adjacent channel interference. Adjacent channel interference is way worse than co-channel interference. I'd rather share a channel with you than fight over a channel with you. So if you have 1, 5, 9, and 13, fantastic, as long as you're out in Alice Springs with no neighbors. But if you have a neighbor on 6, you're going to have a worse problem. But you know what? Wi-Fi still works. You don't find any of these issues because unless you're looking at the tuning part, it just still works. And so like, it works. And then users complain, well, it's slow. Yeah, it's still working. Don't bond channels in 2.4. We saw that earlier. Just this one, there is no caveat. This is don't. No other reason to ever do this. Don't. Maybe if you're in a submarine. You need to choose your access point way before you even start in your design. Where's Use? This one's for you, man. Take the dang generic AP out of your list. You cannot buy one, so why would I ever design for one? It's not possible. Now, there's support for this. Now, here's the reason why. And I get too many people who say, well, I designed, what you want? Well, a Cisco. But what'd you install? Well, an AirHive. Well, no wonder it doesn't work. Well, an AP is an AP. No, they're not. So let's just look. I was very kind, and I removed the vendor names. So here is, oh, by the way, these are all comparable. They're all sellable, except for this stupid one. This is the generic. Look how perfect it is. And I have no idea what these two little pokey things are. I don't want to know what the engineers were thinking when they made that one. But this is generic one. This is how much energy we're putting out. We put out of the AP into the antenna. This is what comes out of the antenna. This nice guy actually takes away energy. He has a negative dBi. Thank you very much. Now, that's not unique. A whole bunch of phones have negative dBi antennas. This guy is adding about 2.2. We got a 4, another 4, and almost a 9. All of these compare and sell in the same market to the same customers. Which one do you think has better Wi-Fi? Even if you don't think about the chipsets and the AC wave 1 versus wave 2 versus any of the other features, just from SNR alone, I'm picking up 9 dB more from this guy than this guy. That's 2, 4, 8 times more signal strength. You're going to, if you look at the MCS table, 9 dB is going to shift me over entire data rates. Everyone's going to talk faster. My density goes up, even if I don't have anything except for that antenna. Again, there's also, think of what it could do if I had a 13 or a 15 dB directional antenna. I could even boost that even more. So the question is, choose your AP first, because you can't design unless you know your AP. It makes a difference. 2 access points in the same area with co-channel interference have the capacity of 1. So if you're designed for capacity, you can't just add another AP. It doesn't work that way. Here's the reason why. So the second slide is just really boring, but it is. 2 or more APs, same contention area with the above the CCA preamble detect threshold, share the medium. Because they share the medium, the capacity is the same as a single. Thus, you don't add any capacity by adding another AP. This isn't a switch. When I add another port, I get another port. This is the hub. If I jack 2 hubs together, I just have a bigger collision domain. If you forget everything else I say today, and remember this, it will be worth whatever it took to get you there. Now, changing the number of APs may, if you properly design them and put them where they need to go and put them on different channels. You might have to go to 20 megahertz channels instead of 40s, but they may actually give you more capacity. May. The change in your clients will always give you more capacity. And this is a crazy one a lot of people have a tough time thinking about, right? Watch. I'm going to give it an example of this. Let's say I had a really brand new AP, 13, AC Wave 2 AP, 3x3, can push 1.3 gig. But I have tablets. They're only 1x1 tablets. They can do 65 meg raw, 20 meg TCP net. Each application that I want, let's say somebody says, yes, we need a 2 meg application. So you pick an application, 2 meg. Each tablet uses 2 meg divided by 30 megabits, which means they use 6% airtime per tablet. I have 200 tablets, do the math, and I need 14 air times. That's a weird word, air times. I need 14 sets of airtime. I don't buy air times, I buy APs. So we say that's going to take 14 radios. So tablets, the answer is 14. What if I just changed my client device? Same AP, I went to a 2x2 laptop. Could do 300 raw, net 150, do the math, and now I only need 3 airtimes or 3 radios. So when you go to your customer and you say, what clients do you want? And they say, all. You go, oh, really? That's going to change your budget, in this case, more than 3x. 3x. Do you think you can afford to buy better tablets? Or do I spend $500,000 on my infrastructure? What drives design most is your clients. You go, but we can't afford them all. Okay, so we're going to do half. Half laptops, half tablets. Do all the math, and we end up with 10. The slow stuff drags down the fast stuff. If I had shown you 3x3 laptops, it would have really knocked your socks off. It wouldn't even be close. You need to know this math. For every customer you ask, this is the important thing to know. Back, you may, by selling more APs, get more density. You will always get better density, faster throughput, better results by changing your client devices. And no one talks about clients, because we don't get paid by the client guys. But that's, well, I guess if you like to sell lots of APs, you'll say, oh, buy the 1x1 clients. No, I have to sell you more. Now the next set aren't rules, they're just kind of statements, things you need to learn. You should know all this stuff. These are just stuff to learn. Coverage is easy. Anyone can do coverage. Put an AP, I have coverage. More AP, more AP. More coverage. More coverage? Oh, I want more coverage, turn up the power. How much power? Keep turning up the power. Coverage is easy, anybody can get coverage. That's the easy one. Hard one's making all the other things work. 2, 4, and 5 gig go the same distance. Have you ever said 5 gig doesn't go as far as 2.4? Anyone? Who said that? 5 gig doesn't go as far as 2.4? Liar. I say it. It's a flat out lie. 2, 4, and 5 gig go the exact same distance. If I had an AP here with dual frequencies, boom, they go off. The radio waves hit the moon at the same time. They hit Jupiter at the same time. 8 years from now, they'll hit Alpha Centauri at the same time. The difference is about receive aperture. receive aperture is on the antenna. Earlier today, someone talked about we have an antenna that's tuned to 2.4 and a smaller antenna because it's a smaller wave tuned for 5 gig. It's got less receive aperture. So the 5 gig antenna gets less signal. How much less? 4 times less, 6 dB. So the 2.4s will always outperform the 5 gigs at the same distance. Now we know the rule. If we want our circles to be the same size, I just take the 2.4 radio and I turn it down 6 dB, and my circles magically are the same size because I'm delivering to the client the same RF that's going to be inside the client. Once I understand how the client works, the difference between the receive apertures, I can make my network do it. If I want my 5 gig to be preferred over 2.4, and you want your 5 gig preferred over 2.4, you need to push more than 6 dB differential. Now I can make the 2.4s less, or I can make the 5 gigs more, but sometimes I run into legal limits depending on the country I'm in. I'm at the max there, so the only place to do it is to take the 2.4s down. Know this one, like in your soul. I was in England last week and I said, you should not be able to convert miles to kilometers. And they're like, what? Because they still talk about miles per liter. Like, you did the liter one, but you missed the miles one? Oh, no, it's kilometers per gallon. No. Either you do them all metric, you all don't. But this one should just be really fast. If I say 100 milliwatts, you know it's 20 dBm. Not a thought, not a think, it's just fast. If you don't, practice and practice and practice. Because you need to be, I don't know the right word, ambidextrous. One hand you can write in dB and one hand in milliwatts. Or if you're a Cisco shop, milliwatts, dB, power level. If you're a Aruba shop, dB, milliwatt, EIRP. Everyone treats them different, but you need to know what the base is in order to think through it. Now this is just some ones you should just know. Association is to wireless, what link light is to wire. If I get a link light, do I think troubleshooting? I should replace the patch cable. Does it cross your mind, you get a link light, you go, yeah, it's a patch cable. I get a link light, oh, it must be the switch is down. On wireless, people go, oh, yeah. Is that me? On wireless, something happens and you go, oh, maybe we should get an AP, maybe it's like, wait, are you associated? If you're associated, wireless is working. If your wireless client has an IP address, how did it get it? If your wireless client has an APIPA address, 169 address, how did it get it? It had to actually associate, trip the link light, say, I need a DHCP, attempt a DHCP, and then fail, and that's how I get a 169. So if you get a 169 address, you have no wireless problems, you have a DHCP problem. If you have an address at all, you don't have a wireless problem. If you have a captive portal, you definitely don't have a wireless problem because you connected, you associate, you got a link light, you got to send a DHCP request, you got a DHCP response, both over the wireless, and then the captive portal came over the wireless and said, welcome to my captive portal. You don't have a wireless problem, and yet all of our customers think, oh, that's the beginning. It's actually the end. Lowering your transmit power does not fix CCI issues. Now some people don't like calling it co-channel interference. They call it co-channel. What is the A? What is it? CCA. It means something else.
Channel access.
No, that they're fighting for the. It's a contention area. Anyway, the problem is, if I turn the power down, it doesn't fix it. It's very easy to show. You can fire up eCal, you put an AP in there, and you say, power's 50 milliwatts, power's 20 milliwatts, power's 1 milliwatt, and the area of don't want hardly moves at all. Your co-channel interference zone doesn't move when you turn down your power. You want to get rid of co-channel interference? Turn off a radio. For your Cisco folks, this means FRA. You want my radio to turn off. Coverage is to wireless what connectivity is to wire. In wire, if I looked at Cat5 cable, what are some requirements? What are requirements for Cat5 cable? Okay, this is the part where you answer. What? Distance, how far? 100 meters. Another requirement for Cat5 cable. What? Twist rate. Not just twist rate, they just can't twist. They have to have one fast and one slow. Okay, now I practiced that. You should just clap. One fast and one slow. Try it. It's not easy. I have twist rates, twist ratios. I have pinouts, near side crosstalk, far side crosstalk, all sorts of things to define whether or not my wire meets. But what's the number one requirement in Cat5 cable? The electrons have to go from one end to the other. We could use, if all we needed was connectivity, I could use barbed wire. It has infinite crosstalk. But if all I needed was connectivity, it would work. But connectivity isn't sufficient in the wired world. I have to have all those other things. In the wireless world, that's coverage. I have to have coverage. It's required. It must be there. It's mandatory. But it is not sufficient. I need to get all the other requirements in there. Clean air doesn't. Okay, how many of you guys are Cisco? Because you're supposed to laugh at that one. They should rename it to be Run Away and Hide from Dirty Air. Because that's what it does. Now, I really like clean air APs. I love the Cognu chip. I used to teach a 5-day class on how just to decode the Cognu chip when it was a PCM, and it's a wonderful spec amp. It does not clean squat. Like you turn it on the AP and you go, yeah, I want to clean air. No, you don't. You just run away and hide. You want to fix the microwave oven that's dirty air? Get off your butt, go down and fix the microwave oven. Your APs can't fix anything. So don't pretend by the mark. See, now you see one of my marketing things coming out. Okay. Increasing the transmit power is a good thing, but it only improves RSSI in one direction. It's also why you're going to cause other issues because if it only has a one-way direction. If I want to improve RSSI, change my antenna. The antenna gain is bidirectional. I hear better and I talk better at the same time. Changing my power only lets me yell, but I can't hear you any better. So again, choose antennas wisely. Cover what you want, don't cover what you don't want. Next, double distance quarter the power. We had the graph over here a little earlier. Had a little nice free space loss curve. When I teach a class, I think I draw that 15 times in 4 days. You can know that. First 1 meter in 2.4, how much loss do I have? 40. 2 meters is what I lost. 46. Because I double the distance, I get a quarter of the power. Now that's the rule for free space path loss. Right. What if I want to double the distance? I'm going to do the reverse calculation. I need to add 6 dB. This is a pretty easy one, right? I design something to go to a spaceship that's halfway to the moon. It takes X dB to get halfway to the moon. How many dB does it take to go all the way to the moon? X plus 6. That's it. Now, it might be a lot to get there, but the second half is always just give me a simple calculation. Lowering your MBR does not shrink your cell size. I've heard people say this many, many times. It does not. The preambles are always sent at BPSK. BPSK is the most robust, really big, huge EVM, so we can punch through lots of traffic. They're sent at BPSK for a whole bunch of reasons, but realize your preamble detect is what's going to tell you about your cell size. Your preamble detect cell size did not change one bit, even if I went to 48 MBR. Co-inference is exactly the same. I might hear you and can't decode you because you turned on, I'm too far away, I can't decode your 48 meg. I can just hear your preamble. And preamble has a length field that's going to make me shut up. Now my shut up isn't as precise as if I hear your duration ID in your header, but if I can't decode your header, I still am shut up. Doesn't change those at all. Oh, that was not what I wanted to do. Know your phi, your physical layer. How it works, what it does, whether or not we're A, B, G, N, AC, AX, wave 2, whatever, know it. If you don't know it, how can you possibly be out there designing it? Know your modulation techniques. I do a little demo showing how to see and visualize what a BPSK looks like. It has a huge amount of resiliency. QPSK has less resiliency. 16 quantum has even less resiliency. And when you get to that picture we showed earlier of the 2024 quantum, little teeny target, which means it doesn't have a lot of resiliency. Who decides which modulation scheme to use, the transmitter or the receiver? Yell it loud. If you're going to be wrong, be strong wrong. Who determines the modulation I should use? Transmitter or receiver? Okay, I heard blah, blah, blah. Who votes receiver? Who votes transmitter? Okay, we got a room full of smart people and you're divided on something that's critical on how Wi-Fi works. 100% of the time, it is the transmitter. Receivers have absolutely nothing to do with that because Wi-Fi is a one-way protocol. If I'm a transmitter, the only thing I know is about me. I don't know anything about you. The only thing the receivers can do, and they have no choice in the matter, I can't change them, is if they can't demodulate it, they don't send an ACK. If they can demodulate it, they send an ACK. That's not a decision, that just happens. So all decisions about what to transmit happen at the transmitter. So when the client talks to the AP, he chooses. When the AP talks to the client, the AP chooses. Every transmitter is making every decision using a choice of modulation, and they do it dynamically on the fly. So, if I want to design for 64 QAM, I need a certain amount of SNR. Now those of you who've been to my class, don't answer the question. Everyone else answer the next question. Who in your organization controls S, the signal strength? How do you control S in your environment? How do you make stronger RSSI at every location in your building? You go in the controller and you turn up the power. So whoever's controlling the APs in the controller or standalone, however you want, is controlling S. Who controls N? The pineapple. No. N, and Mark had a slide up this morning, he didn't emphasize it, I wish he did, that showed preamble detect in the protocol by spec in the protocol is neg 82. Now you can adjust that, and some vendors push it up to 85 or 86. If you're a Cisco shop, you can go in the CLI and go to RxSOP and move it, but the protocol says 82. Energy detect, 62. Meaning, 20 dB differential, that's 100x. We are 100 times more sensitive to other Wi-Fi than not Wi-Fi. So when I said who controls N, it's the same guy who controls S. My S is your N, your S is his S. And for every AP, you're on my channel, I'm 100 times more sensitive to your Wi-Fi than to the microwave oven, or the Bluetooth, or those other things we try to hunt down. It's Wi-Fi is harming Wi-Fi. The number one cause of interference in Wi-Fi is other Wi-Fi. And we control it. So if we want to control this to get up so we can talk fast, we need to control the N. What do you say? There's only two things we control: noise, signal. That's how you do it. You fix it, but you fix it yourself. Know your protocol. This is higher up the layer. Know the PHY layer. Now you also need to know the MAC layer. Know what a client's RF is versus wire. And when I say know this, you should know this instantly. Let's say you need to know MCS, because MCS can determine not only my modulation scheme, but my coding scheme, the channel width, and whether or not I use guard interval. What data rates I'm going to achieve from there. What my IP address is and whether I got it. What my net throughput on the network is. You need to be able to compare these fast, quick, and it's like brain dead simple to find out if there's a problem. Ready? Here's a site I was at in Dubai. I was on this hotel Wi-Fi. My laptop does a 1.3 gig, but the AP was offering 867. That's what the AP said. Hello, I can do 2 spatial streams, 80 megahertz channels, dun, 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 equal 867. That's MCS 9. That's a 256 QAM, 506 coding, short guard interval, 80 megahertz wide channel. So that's how my NIC packaged the next frame was with all of those pieces. And it was sending them continually, and that is almost rock solid. This is an MCS line down here. My MCS 9, rock solid. Good Wi-Fi or bad Wi-Fi? Could my NIC go any better? Now if I had an AP that was better, and I had the 3rd spatial stream, maybe. But where I could not have any better Wi-Fi. And my download speed was 1 meg. So I go to the front desk, and I said, yeah, I was just on the internet. I know, everyone complains about our Wi-Fi. Did they have bad Wi-Fi? They had fantastic Wi-Fi. They had bad backhaul. Now I picked this because it's a very obvious example. Seems got a lot. On your phone. What's the MCS you're connected to right now? What's your coding rate? What's your data rate? Are you right now, at any point in time when any user makes a complaint about Wi-Fi, you should be able to go to that device and say, is it a Wi-Fi issue? If it's a Wi-Fi issue and I'm running MCS's 789 or 567, whatever you have is normal for you, and I'm staying in the 567 range, I got great Wi-Fi. Anything else they complain about cannot be Wi-Fi, because every transmission for every frame makes a decision. Did I send the right way? And if I did, I got a MAC. If I didn't, I'm going to change my modulation. And so if I'm staying at MCS 7, I got MCS quality 7. There's nothing wrong with the Wi-Fi. Your troubleshooting skills should be totally about, is it maintaining what it's supposed to? If not, it's a Wi-Fi problem. But if the Wi-Fi is working, it's not a Wi-Fi problem. So what we want to do, I'll skip ahead here for a second. All 802.11 transmitters choose modulation, coding, channel width, and guard interval. The transmitter chooses, not the client. So we want to know how this happens. What is the process? Got a nice little picture here. And this is MCS. It has coding, it has SNR, it has RSSI. It has all the details on one page. You can get a copy of my webpage, I tweet it all the time. So, let's say my laptop, 1.3 gig, talks to an AP and the AP says, I can do 867. In the association process, I tell what I can do, this is what I can do. Once it's done, it comes back and says, okay, this is the fastest I can do, 866. Now my laptop has a table that says I have to stay within this group. My laptop only has to remember one table. The AP, on the other hand, has to have a table for me, and you, and you, and you. Every single table has to be different. And then within that table, my roaming algorithm, my algorithm to tell me how am I going to package the next frame, is going to go, okay, let's try this 867. I've associated, first thing I want to send is a DHCP request. How do I bundle the bits in the DHCP request? Well, I'm going to put them in 256 QAM, little teeny dots, small EVM. I'm going to use 5 to 6 coding. Think of coding as parity bits. I'm going to send 6, but I need 5 to carry the way through. If I was 1 of 2 coding, I would send 2 and need to keep 1. That's 100% spare. Down here, I have a smaller spare. I'm going to send it in an 80 megahertz wide channel, which means my SNR is down. I'm purposely choosing the lower SNR because when I go 80 megahertz wide channel, I'm listening to 80 megahertz of noise. If I go to 40, I would pick up 3 more SNR, 37, 34. If I go to 20, I'd pick up 3 more SNR, 34 to 31. So I picked this on purpose because I want to go fast. I'm at a conference, don't ring. Okay. Now, if I send that and it works, great. If I send it and I fail, what do I know? Nothing. It could have been a collision. Could have been interference. Could have been I picked the wrong channel. It could have been I picked the frequency. Could have been I had the wrong modulation. It could have been the coding. I don't know what it was. All I know is I tried it, didn't work. So I'm going to try it again. Now every vendor, again, this is transmitter. So AP vendors have to play the same rules. Client vendors have to play the same rules. I sent it at this. It didn't work. What should I do? Well, I'm going to try it again because I think maybe it was just high contention. A lot of people talking. I'll try it again. I'll try it again. Maybe it's a collision. I'll try again. Now every time I try again, my random backup timer gets bigger, so I have to get spread out in time to not bump into other people. And by the time I went bump, 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 I went all. I have a huge random backup timer. CW max, if you're into that kind of term. It didn't work. Maybe I should go and change modulation. So instead of 256 QAM, let's jump up to 64. So now I'm going to be sending it over here at 780. That's quite a hit, but, sorry, I went up to 650. I went to 64 QAM. Still 5 to 6 coding. Data no app, data no app, data no app. What should I do now? Well, some vendors go up, 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 over, up, 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 over. And they have a pattern. Some go up 2, over 1, up 2, over 1. Some go 866, fail, 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 ding, all the way up to 6.5. And you laugh, but it's actually a smart move. Because what it's saying is, I might be on the wrong AP. Because I associated a long time ago, and now I actually have a frame, I could have moved out of the AP zone. If I cannot use BPSK, hugely resilient protocol, 1 of 2 coding, double bits just to deliver 1, it's 100% spare bit. 20 megahertz channel, which has the highest SNR, and no low, long guard interval. I cannot make Wi-Fi go worse than that. If I can't make that one worse, wrong, because I'm on the wrong AP. There's all sorts of patterns of this. APs have patterns. I'm talking to you. Clients have some smarts too. Oh, the last time I was at my home on my couch with my iPad talking to my home router, the sweet spot we found was here. I'm going to go back there because I have a little heuristics memory. I walked through a portal in a stadium and somebody kicks me off because they don't want me on that AP. Stupid AP, I'm never going to go back to you again. There's blacklists and whitelists and graylists and all sorts of things about how to move around on here. And all you have to do to figure it out on your own, put a packet capture on and walk around and you'll watch the decision yours makes. Yeah, crazy part is, they always don't make the same decisions. This is complex stuff. And then our users go, yeah, the Wi-Fi is slow. Really? What does Netflix need in order to get a movie to you? 2 meg for SD, 4 meg for HD. Our slowest is 6.5. The worst Wi-Fi possible handles that. What about voice? What does voice need? 64K. In old B, 1 megabit data rate, I could push 15 voice calls simultaneously over 1 meg. Yeah, right. It's not about this. So when people say in a hotel, yeah, Netflix is slow. Yeah? Even if we had terrible, that's not the problem. Now the problem is contention. How many people are sharing that? To get more density, we get people to talk faster. Not more APs, we get people to talk faster. You also need to know your regional codes. Back there. I have 22 seconds, man. I'll finish. Know your regional frequency to find out where you are, what you can do in each frequency, and every vendor, whether you're Aruba or Cisco or Ruckus or Extreme, has tables to tell you how to play with this. They have to follow the rules legally. So you don't have to learn this, but you kind of do. Because if you don't know it, how are you going to design for it or troubleshoot it? So know what they are. Oh, one last one. There's a bunch of RF requirements. You need to know the RF, and that's most of the ones I've talked about today. You also need to know about the non-RF ones, and these are vendor specific. You're not going to adjust these in Ekahau. You're not going to learn them in a CWNA class. You're not going to learn them in an Ekahau class. This is you learn by going to an Aruba class or a Cisco class or a Ruckus class. Also, very, very, very important. I just didn't talk about them because it's a whole set of rules that's vendor specific. And that's all.
Keith, it's great. Okay, summary of Keith's presentation. Do not play Lego with Keith. No, you need to buy Ekahau, that's the summary. So next up we have Aaron Scott presenting to us. He's from Aruba. And look forward to this presentation, mate. While he's setting up, we'll save the questions, I think. We're a little bit behind on time, so keep it for the panel discussion, guys. Oh, perfect? Perfect on time? Okay. He's going to clean this Lego up, is what we're going to do. Okay, go ahead, mate.
Can people hear me? Hi everybody, hope you remembered everything that Keith said. We're going to break some of those rules here. Stadium's a little bit different than everything else, right? Not coming through the mic.
Maybe you need it a bit higher and I'll come here. You've got the switch on.
Oh, that's working, is it? Maybe it's getting stuck in the beard.
Put the microphone in the beard.
Yeah, we'll just have to hold it.
Okay.
That's okay. I think it's a big deal. Awesome. Okay, so we good?
Yeah.
Oh, there he is. Yeah, okay. Is that better? No, we're all good. Hi. So, yes, I'm here to talk about stadium Wi-Fi, but everything that Keith sort of said is true in a stadium, and everything I'm going to say is kind of true everywhere else as well. Stadiums are just more like a normal office on steroids, and everything's a lot more complex, but it's the same type of rules, yeah. So we're going to break some rules, we're going to follow some rules, and you're kind of going to see. Now, when you start a stadium, the first thing the stadium owner, or whoever's going to run the stadium, is going to want to know is, how fast am I going to be? I want about the best experience, it's got to be the best thing for the end user, it's going to be awesome, and you're going to quickly find out that that's not how it works. So, what we have is, you go and see a customer, and they're going to, Keith already talked about, you go and find the requirements of the place, right? So you go to an office and you get the requirements of an office space, and the layout's the same. Everyone, you kind of know what everybody's going to be doing across the entire facility. When you have a stadium, things are very different everywhere. So you're going to have different requirements for different parts of the stadium. What you do in the bowl is you sit there and you take photos, you capture some video, and then you upload that to YouTube, Twitter, wherever it's going, right? So there's a lot of upstream traffic, but people don't necessarily move about, they sit still. Things like the concourse has completely different set of requirements. People walk, they move fast, they go to the toilet, they go and stand in concession lines. So there is some of the same sort of things where you're standing still doing things on a mobile device, you're standing in a concession stand, but a lot of people move. So there's a completely different set of requirements. Things like when you sit down in a bowl, you know that there's going to be X number of people in the seats around you. If you're planning on spitball a number, an AP for every 100 seats, well then you know there's going to be 100 seats there, and that's going to be it. But in a concourse, you might design an area to be covered, but then there could be 2,000 people walk past, and that's completely separate. You've got to think about in-rush, out-rush. There's a lot of different things in the concourse. People move. Suites, again, very different again. A handful of people. Actually, suites generally maybe 20, 30 people in a large suite. They could be doing things like multicast video being streamed to them, and again, those sort of higher end suites. Media, it's even less people, it's like 2 or 3 people in a booth, maybe editing video. Why they'd be on Wi-Fi, I don't know. It should be wired, again, they're not moving, plug them in. There's another place like back of house, you know, service corridors, that's really just roaming. People moving around, getting around the facility, again, another completely separate set of requirements. This one's the weirdest one. When do people arrive at a stadium? They don't all arrive at the same time, do they? No, there's generally games on before it, and you dribs and drabs as they come in. So your entry gate design isn't for that. It's for when everyone necks off. They all rush out. You empty a stadium of 70,000 people, they're all getting out straight away. And so being able to handle the rush of that many people running through an area and still maybe connecting. If they've been connected in the bowl, they're going to be connected everywhere else. So there's a lot of different bits. So when you go and do things around your RF models, you have to do these separately. You can't design and go, all right, I'm going to do an AP per 100 seats. Well, there's no seats everywhere. So you end up with different designs. But where's the primary part of a stadium? Any bowl, yes. So that's where you start, because everything then relates off that. So like when you do the office space of an enterprise, you don't start with the toilets, right? You start with, well, it's a critical area, but you don't start there, you start where people work and then work your way out. Same thing in a stadium. Yeah, Keith put up that wonderful picture of the hotel with excellent Wi-Fi, but horrible backhaul, right? how do you gauge how much backhaul you're going to need for 70,000 people, 100,000 people? You need a lot, right? It's a massive amount. So trying to figure that sort of calculation out is not taking that sticker number of your data rates, 1.3 gig, and going, everyone's going to get 1.3 gig, times that by 50,000 people who are going to connect, and I need an awful lot of gigs of throughput. No, that's not how it works. We factor things in to that. You know, everything is based on sort of a restricted version of an enterprise. Keith talks about not having co-channel interference. You can't avoid that in the stadium. You can do your best to minimize it, but you're going to have a lot of it. You get to use every channel you can. Every channel depends on where in the stadium you're putting APs. Outdoor APs in Australia can't use Uni 1, so 36, 48. So the number of channels will change. So this calculation change is based on the area. So you're going to do those areas that we talked about before, and you're going to do a calculation for each of those. So things like your number of channels, your average throughput is based on the expected mix of devices. Least capable, most important does not exist in a stadium. It's whatever they bring in. Every fan should be able to be connected. So it makes doing those types of calculations and testing, right, am I getting the right signal strength in the right locations, very difficult. You will probably go and borrow Keith's Galaxy S3 and test it on that. Because depending on where the stadium is, how much money people have who go to the stadium, the mix of devices changes. So this average channel throughput tends to be kind of pegged around that 30 megabits that Keith brought up from a 1x1 device. You might get more than that, but you might get less. And then the reuse factor is how many times can I reuse these channels in the stadium and not have co-channel interference? There is none until you can prove it. Don't get to use channel 36 again in the bowl until you can prove you can do it without CCI. You're going to have to put them in anyway. You have CCI, there is no deleting it out of the bowl. So, this factor is sometimes hard to calculate. How many times can I reuse it again? In a big stadium, maybe like a MCG, something like that, like a big football stadium or cricket ground, that is a physically bigger stadium. Depending on how the RF is designed, you can get a fair chunk of reuse out of that. So you get that increased throughput. But this gets done for all those areas. Your bowl, your concourse, all of it. But you don't just add them together. You add them together, you're going to get a very, very big number. Everybody, if they're in the bowl, they're not on the concourse. There'll be some in both, but you're not going to get it all. So it's a balancing number. But this gives you that guide to fix your backhaul problem. In your stadiums, everything is redundant. Stadium Wi-Fi going down during the middle of a game doesn't just impact fans, it impacts media, it impacts everything. So there is that. This is a guide. So when you go to the customer and say, how much do I need? Well, you've got enough idea. Right? What does a stadium design look like? This is, okay, it's still very similar to an enterprise. We just don't have a roof in this picture. But in an enterprise, you use walls, you use pylons, use everything you can to get channel reuse. You try and control where that RF goes, use directional antennas. We do the same things here. We just don't have 30 access points on the floor. We have maybe 600 or 700 APs in the bowl. So when you look at it, we get in a bowl, this one has no roof, so we can shoot stuff up. If we shoot things up, other APs can't hear them. Therefore, we get channel reuse. The client, so if we're shooting an AP up here, the clients over here are not going to hear that. They will hear the other client, but there's nothing we can do with it. We can control the network side, right? So bowls, we tend to shoot out of it. Now you'll see when we have a bowl with a roof on it, it's the complete opposite when we shoot down. Things like suites. So like an office suite. Most of the times you will use an Omni. It's easy, you stick it in the back of it. But what you don't want is the coverage from here being seen all the way across here. So you push it to the back and you try and control it. It's all about controlling RF. It's the only way we can do these things and make them work. Concourses. Down and out. Get it away from the bowl. Remember, we designed our bowl first. Everything else we want to get away from it, work it away so we can get some reuse. And then your outer perimeter and stuff goes directly out. You'll notice none of these are pointing at each other. We're eliminating as much co-channel as we can. You won't get the throughputs that you're after, particularly if you've gone through the total system throughput calculation, come up with a number, and then you go and install it and you get a fraction of it. It's probably because you've got way too much co-channel. Your throughput's low. Now, there's two sort of major designs you can pick. In an office space, you hang them off the ceiling. You don't hang them like clocks. In stadiums, you've got a couple options. This one, beautifully modelled by Chuck, is under the seat. That's the one shooting up. We have an AP in the box shooting up. You notice things that I'm going to talk about in a minute, this wonderful tube. And you'll see why that's kind of important when I get to another slide. But these are designed to handle shooting up through the body. We use the body to attenuate the signal, therefore we don't have as much coverage out of an AP, which is what we want in the stadium. We want nice and close. We want plenty of signal for those people there, but we don't want that being heard 100 metres away. That was a Levi picture here. When you got a roof, do you want to shoot up? Because it's going to go up, it's going to hit roof and then scatter and go everywhere and annoy everybody. We want to shoot down into the big bags of water that are people, let them absorb it and have radiation sickness. We'll shoot down. And then you use whatever you can to mount off. Under a seat you've got plenty of concrete. Up here you hopefully have some sort of gantries and that sort of stuff to hang off. And then we use highly directional antennas to give you some control. We're not going to put Omnis 25 metres up in the ceiling and cross your fingers and hope for the best. We're going to control this with very directional antennas. Looking for ones with very controlled side lobes. If you have 100 APs, 200 APs running around the roof, they're kind of within your 2 metres of anything. You need to control that so they don't hear each other. And so we tend to split them up. You have something covering the low bowl, and you work your way up and you spread them out. That's your general type of rule, and you get sort of attachments like this. AP at the top, a nice long pole down, antennas hidden below the entry, keeping it away from the big chunks of metal. Now, sometimes you can't use an under the seat even though you have no roof. You have to think of other things, right? If you have no roof and you can't go under the seat, it's very, very difficult. You don't need to mount on. What do you do if you have a roof and you want to get the most out of it? Do you use overhead or do you use under seat? Yeah, generally no. In our experience, the client will see the one overhead as much cleaner and not pick up the one under the seat. But there's always reasons why you don't end up with one or the other. You might go in, now this one is getting a roof. It's a material roof that is transparent to RF, so most of it will, unless it's hitting the structure, it will go straight through. So you could do under seat. And most customers, when they build a new one, they will want an under seat because they want the best performance. But there are so many little decisions that impact what you end up with. If it's a pre-existing stadium, can you get under the seat? Is there, if it's a brand new, can I get the coring done as part of the pour of the concrete? So my cables run through the concrete and I put my AP in a little box under the seat. One big problem in something like this when it's getting built, and they want the plan before they build it so they can put the coring in for the concrete, where do I put my APs? You can use Echo and you can plan a lot of this stuff. But what's in the concrete? Yeah, and how much of it? Is it built like Keith's 2 pitches? Is it built like that one? Was it kind of dodgy and fall down? Or was it built the one that's going to stand the test of time? You don't know, because that's not in CAD drawings you've got. So sometimes you have the best placement and then you end up with an AP that is physically moved and you have ducting. Back to the original, which is kind of that Levi's one, the AP was slightly off from where it was planned to be. Some places don't allow you to have ducts. Some places have vandalism issues. Particularly if you go out west of Sydney, where they tend to take ratchets in and under seats and throw them at each other. You get vetoed on doing under the seat because you can't put anything under there. Someone throw a flare at you and they'll rip that up and they'll throw that at you too, just because you support the other team. It happens out there. Yeah. So suppose you could get all that sort of stuff right. Can I still go under the seat? Is there enough room under here to fit an AP? Is the mounting of the seats going to get in the way of where I want to put my APs? This one, there's heaps of room, right? This one, same stadium. There's nowhere to fit that under the seat. To add on to this one, this is removable. These things compact back and move back to give more floor space on the stadium. Where do I put an AP? How does it then collapse back? And then the big one, under the seat costs more. So, that was a picture for UC. It's not even paying attention though.
Thank you.
Don't you like that one? Under seat costs more. But then, got a pose for it?
Thank you.
Alright. So budget can veto pretty much every decision you make. And you'll be forever changing it. So you might go, right, we can fit under the seat in the budget, and then as the project progresses, everybody else adds their bits, the contractors, the cabling guys, all those guys add their bits, and then you end up with miles over the budget, then you go and restart again and blow away everything you started, and go again. Yeah. Generally, you would look, oh, I had a picture here. It's not there anymore, but that's okay. I did say that floor plans aren't always true. You're gonna get your requirements. You're gonna ask them for the floor plan, so you go and start doing predictive in How and that sort of tools. This is a floor plan, if you didn't know. This is the concourse level of a stadium. So, not worried about the concourse, I'm looking at the lower bowl here. This all looks fine. I could, as far as this floor plan is concerned, I could go and put under the seat on it. But it's for the same stadium from those pictures earlier. This bit is all removable seating. Can I put under the seat there? Probably not. If I don't put under the seat there, how do I cover those seats? Can I do under the seat everywhere else and then do some sort of directional on that? The roof's generally 20 to 25 metres high. It means you've got a coverage area, even on a nice tight antenna of about 25, 30 metres. This is 6 rows of seats. So you kind of veto the idea of doing combined on that one. To make this one worse, as another way of ruling out under the seat, all of that bit is built directly on Earth. There's no space under it. So when you go to the customer and say, can I get under the seats? And they go, yeah, sure. I just didn't tell you that it's only for this bit. All of this bit, you cannot get to. But of course, you don't know this until you go there. So, you take all this and you realise, okay, I'm going to go with an overhead. This is a stadium that's in the middle of being deployed at the moment, but we ended up with overhead, purely across all those things. Vandalism was a concern, budget was a concern, can't get under the seat, removable settings, all those things impacted that choice from the customer's expectation that it was going to be the best stadium Wi-Fi ever. So we were starting to compromise straight away. So you end up with a design similar to the one that I showed on this slide before, where we've split it up with this. And then you take all that and you go and stick it in Ekahau and you start to model stuff. You go and put APs on the floor plan and there we go. So you end up with, that's about 150 odd APs. But if you marry this up with this one, we have an inner ring, a ring in the middle, which are offset, so horizontally offset. So AP1 as you go around the stadium, into AP2, and then one more. And that's what we started with. So you end up with that, and then you start to look at what sort of coverage do I get. We get our concentric rings of coverage, and we work our way out so that we have clients with high SNR talking to the right APs. Problem number one, architects. Not only did they not like the look of this, they changed the stadium so that we couldn't do it. This became material, not a solid surface. They said, all we can do is mount off a gantry up here. So, even though right at the start, we probably started with a RF design that was awesome, it was going to be under the seat, fantastic, and then we work our way down, we end up with a design that looks like this, and then the architect comes in and ruins the whole lot of it, and you start again. And then, there's some valid reasons. This was going to come material, why couldn't we just move the APs up to the framework? Serviceability. How do I get to that? And the only accessible part on the roof is this gantry console. So you then end up with redesign number 3, and hours worth of work of moving APs around and making sure that when you end up with 3 APs pretty much attaching at the same point but staggered horizontally, that you get enough of that 2 meter clearance to keep them so they don't interfere with each other, even though they're on different channels. So there's a lot of thinking as to getting that sort of flow to work. What you end up with was essentially the same thing. Now, on this stadium, I'm kind of jumping between 2 stadiums, so just bear with me a bit. This one has a roof that goes all the way around. What happens if the roof doesn't go all the way around? How do you cut seats? This one kind of gives it away where it is. With a logo. What about this bit? Look at an enterprise, you've got roof. Even in this place, you can drop things down off the roof. What do you do when there's no roof? We have our removable seating all the way around the front. We have nothing to mount off. We have to get inventive. Do we go at the front fence and point back? Can't really do that because the seats come out. But if we move it up to where the seats don't come out, can that work? No, because what about the people on the removable seats when they're in? Do we mount stuff right behind them and shoot down? Well, that's about 20 rows of seats. That's a lot of water bags to shoot through. So you start to look for other things. What else is floating around here? We have lighting towers. We have the scoreboard. But all those do is look at the direction those are pointing in. One off say the lights down there. All the other design was for the overhead is pointing away. We're breaking everything by pointing forwards. We're almost intentionally causing co-channel interference. An AP up there will be heard over here. very, very well. But if you don't put anything up there, all the little people down here in the cheap seats have nothing. Well, it's basically correct. You bought a cheap seat, you get best effort. Best effort's not great. So, there's other things you can tell from this picture. This stand from here around to here was built in 1990 something. This stand was built in the 2000s. It's a completely different design. There is one big problem. I think we're supposed to get a minute. This bit here overhangs the lower bowl. As you can see, this hangs down over the top. So there's about 5 rows of seats that cannot see anything mounted on the ceiling. Can't see the ceiling at all. So you then start to come up with these types of installs where you are specifically burying something up near the concrete. So Keith said keep 2 meters away from things, well we didn't. This is right up here because I don't want this guys down the front here seeing this AP at all. I want them talking to the ones on the roof. That's what we've designed it for, it's what we've engineered it for. We want this guy to cover 20 times 5, about 100 seats through there. And then you end up with all those around. Yeah, there we are. Just invest in it. Sticking stuff on the roof isn't just as simple as taking an AP up and clipping a mounting bracket to it and throwing it up on the roof. Things need to be engineered. There are regulations on the roof, there's safety things. How do you get the cables up there? This was an early prototype of a roof mount for the same stadium. Cable tray, AP mounted, the antenna cables and power cables come back through, and you get a second version of it, and then a non-powder coated final version where the AP is mounted on the roof. AP cables run down the steel pipes and connect to the antennas. That's a cost you probably don't think of when you're designing the solution. How much does that cost times 150 of them? It's a lot of money. I saw custom engineering for this sort of thing. Sorry? And stainless. The other thing to consider is cable lengths. Not so much the Ethernet ones, the electricians can take care of that. Put more switches in, we'll make it work. The cable length from here to an antenna. When the antenna sits over the edge, there's a pair of them, this thing. Those, when you go longer than 2 meters, at least for Aruba's outdoor APs, you need a lightning arrestor on every cable. That adds up real quick. So if you can keep the cable lengths to 2 meters or less, and it just has to do with conductance of the cable, you can have a lot less cost. It does mean another engineering issue of moving the AP closer to the edge. If you could have 6 meter cables and not be worried about the loss, you can stick the thing right back here behind the safety guide wire and everyone's happy. It's not how budgets work. Concourse. This was our first guess. Directional, when we're putting down and out the concourse, we have a directional pointing away. We're using things like the steel beams to shield that from going back into the box. Remember, we did our bowl design first, then we're working our way out. We have our AP off here, we have another AP up here. Who do you reckon vetoed this design decision? No, electricians. They didn't want to run cables this far up. They had designed cable trays to run at this height, not all the way out there. They didn't want to break out and go up, that's just an added cost. Things get expensive. So then you respin your design again, and you take this guy off here, and you try and put him down here. So you end up with directionals and omnis, trying to cover different things. Just to clear things up here, the blue things are directional, green things are omnis. So you'll see these ones are directionals pointing out, The omnis are hidden in the facade so that they cover the patrons at the concession stand and not really much else. They don't get that much further. They're nice and low, so they're going straight through the bodies. Yeah. This one's simple. We have a single set of concession stands running the whole way around on the outside. That's not how all stadiums work. We have stadiums like this, which has a concession stand running through the middle, and we have two concourses. Concession stands are double-sided. They go on both sides, therefore coverage on both sides. One problem you have, on the inside, from here to here is 3.5 meters. But there is zero signal coming down from the roof. So again, we break this rule. Buried up here, so that we're using the concrete to control the RF and shadow it out, so we don't get people in the seats down here using the APs that we don't want them to. This is designed to handle, I guess, the less density. It's designed to handle the people out the front of the concession stands, and the people that are still in the seats can still do their thing. So you end up with these mixed designs, but you're using the structure as much as you can. Like in an office, you stick it up on the roof and you've got clear space and everyone can see it for ages. You don't want that in a stadium. When your stadium has 600 APs and you get to use 21 channels, you want control. Cabling runs do make a big difference. This is the outer concourse. The original design was to put an AP on the wall and shoot it out. Well, as the best practice of keeping the Wi-Fi pointing out of the stadium so it doesn't impact. As you go around the curve, everything points out. Things don't see each other anymore. Cabling costs to run a cable out and around this pylon to an AP and then get it going around the next pylon in and out makes things way too expensive. So you end up compromising and moving APs. You slide it out and you end up with an AP out here because the cabling can just run straight line around the outside, lowers the installation costs. But again, that's tweaking your deployment quite significantly and you will re-spinning this design over and over. Service areas look like this. This is the same stadium, but they look completely different. This one has a cable tray. This one has a lovely drop ceiling. There are other parts of service where there's no roof at all. And so you start to come up with other types of designs. Drop ceilings are easy, but you can get away with a lower. Keith wants us to use high-end APs all the time because they work better in those scenarios, but when you've just got clients walking down a hallway, and we're going to break two rules here, cheaper APs and in a hallway, but they're only walking down a hallway, there's no rooms, right? So maintaining that. Break it, yeah. So those are generally a little bit easier. This one though, it's a change room. When you look at a floor plan, you can see a lot of, if you have CAD drawings, you can see things are concrete or they're cinder block or they're drywall type of thing. This has a concrete beam. This is down in the very, very basement, so these are cinder block walls. Anyone know what a cinder block wall generally blocks? You would know. How much DB? Big loss. It's concrete filled cinder block. And some Rio involved too. So, planning on an AP in the room, and then you go expecting coverage on the other side, you don't get it. Well, because you need to take ample samples. Visit the site, and you'll see stuff. And even after you do all of this, and you get your 10th version of a design, when do you think things get deployed? The stadium could be years. So your design can be completely different to what you actually install in the end too. But when you waited a long time and the contracts are all signed and they've built enough of the stadium, if it's a new one, to install stuff, you've still got stuff to do. If you're the installer, you have to aim antennas, and this is from Scott Lester. Had a great little blog, there's a link down there, but on how to build this little aiming tool. Flips over the antenna, got a laser sight, points you where you need it to go, you adjust the tilt until it's aiming in the right spot, take it off, put it on the next one, and away you go. And so aiming, well, say it's 150 APs on the roof, 2 antennas for every AP, 300 times you've got to do some adjustments. And every time you hit this one, electricians can't follow rules. What was it? They can't get it within a metre accuracy, don't expect it, Keith, was that? Yeah. In a stadium, because it's such a highly engineered solution, you kind of want them to put it exactly where you want it. It doesn't happen. But so you're always updating your model as well. And you're going to walk around with a sidekick, please. You're not listening, I'm not going to need one. Verify that you're getting what you expect. Of course, you're going to adjust that for your Galaxy S3 that you borrowed from Keith, and make sure that that sees the signal as you expect to. And you get the right roaming and you get the right cell edges and the top. Now, after it's installed, is it ready to go? No. You've done all this testing when the place is empty. You need to test it when it's half full, 10% full, 100% full, all of them. And so you spend the next lot, as you see here, he's not paying attention if he is. You spend the rest of the time tuning, like a mechanic, yeah? And you're going to continue to do this. It's going to take a while to get it right. Yeah, you can have it. Yeah. This was about a week's worth of Photoshop after this. But yeah, tuning happens all the time. It's not sort of you set it and forget it in the stadium. Every event you're going to find something different. Every event has different quantities of people. It could be a completely different type of event. You could have a concert on the ground, and then you have to come up with a different sort of solution. Certain APs will be on, certain won't be. There's a lot of tuning that happens. It's not something like an enterprise. You bang it up, and then maybe every 6 months you come back and do a survey and double check that everything's good. Every event requires something different. Yeah.
Up there.
Yeah.
Otherwise, they're down here. You're shooting from the back. You get
Yeah. Yeah, there's so many things you have to think about when you do a stadium. It's not, I'm sitting at a desk with a laptop. I have, people don't sit still. People stand up, sit down, there's all sorts of different things. But everything that you do in a stadium, everything kind of was the same. You have the budget constraints, you have electrician problems, you have the lovely architects that everybody loves. All those things are the same in enterprise. We just have to do it with a lot more thought and engineering, I guess, when you go for that bigger scale. But it's all the same stuff. You just get to break more of Keith's rules when you do that sort of thing. That's it, thanks.
Thank you, Aaron. So, what did we learn about Aaron? Except that he doesn't like electricians or architects.
Architects are one of those.
We learned that he breaks all the rules, but he still uses Echo. Okay, guys, so I think we're taking a break now. How long is the break? Till 3:20, and then we're going to get all the presenters back up here, and you get to drill them. You get to drill them as long as you want. So, and then we'll go beers after that. So back at 3:10, guys.